Welcome. This is the module 9 and lecture 41. This is the first lecture in module 9. In this lecture, basically, we will discuss injection metallurgy. And before we start that, we talk about the inclusion and discontrol first. Okay. And here we will talk about first the sources of inclusions in steel and then inclusion modification, because some of the inclusion, those inclusion that cannot be removed from the system is modified by calcium treatment, and such that they doesn't have very adverse effect during the further processing of steel. So that is called inclusion modification. We will talk about that, and then LD slag carryover in ladle and inclusion and its effect on inclusion. Then ladle refractory and also effect associated with the inclusions. Okay. Now, sources of inclusion, there are basically two types of inclusions are observed. One is called the endogenous, another is called the exogenous. Endogenous means that evolved within the steel melt by in situ operations. Okay. So that is the basically produced by the chemical reaction between the impurities, because in the steel you have some impurities, all known impurities, and then these impurities can react with each other and then they can form some inclusions. And mostly there is the oxide inclusion is very major inclusion, because of deoxidation it is produced. And then precipitation during solidification. During solidification, as you know, that is the solubility of the impurities in the solid steel is much less compared to that solubility into the liquid state. As a result, during solidification, the impurities are ejected from the liquid and the solid liquid interface become enriched and enriched with the impurities, and these impurities then at the solid liquid interface they exceeds much beyond the solubility product for different compound formation. As a result, different compounds get precipitated. Okay, so those are also inclusions, and those are also endogenous inclusions. And then major inclusions are like basically oxide inclusions are major, and then you have sulfide, carbide, nitrides, oxysulfides. These are the various inclusions are there. And endogenous inclusion, usually they are small, because since they grow by nucleation and growth process, they are usually small, numerous, well distributed, and their composition are basically governed by the typical composition of the steel. Okay, so and typical of steel composition. Okay. Exogenous inclusion means, as the name suggests, it is coming from outside. That means one is that mechanical and chemical erosion of the refractories. The refractories can, because the liquid still move over the refractories, and depending on the starting action, the shear stress at the refractory can be very high. And also the refractory can be under the thermal shock, because if thermal shock resistance is not good, then spalling can take place, all these things can happen. So that is called the mechanical erosion. And then chemical erosion is the refractory can react with the liquid metal, slag. As a result, they can participate in the reaction, and then chemical erosion also can take place. This is exogenous. And then you have slag entrapment, that is the sum of the slag. During the starting, they can be entrapped in the liquid metal, and then they cannot float up, and then they can be entrapped into the steel. And then oxygen pickup. Oxygen, this is the slag entrapment basically will take place at the latter stage. Okay, small tiny slag droplet can be entrapped. And then oxygen pickup through the atmospheric interaction and oxide formation, basically during the timming of steel from the ladle to the tundis. And if they are exposed to the atmosphere, then there is oxygen pickup. There is the chance of oxygen pickup is there, atmospheric interaction and oxygen pickup, and then they can develop various oxide information later on. Usually these all exogenous inclusions are large, scarce, random, and also very irregular, right? Irregular in shape. But you cannot, there is the exogenous, endogenous. This differentiation is difficult sometimes, because sometimes endogenous inclusion can also form over the exogenous inclusion, because exogenous inclusion sometimes act as a nucleation site over which the endogenous inclusion forms by precipitation, like that. So thing is that, and then also there can be a compositional difference from center to the outside. That can be a difference because different methods they are evolving. So basically, so complex non-uniform inclusion involving both exogenous and endogenous inclusions are also possible. Okay, these are the source of inclusions. And then next in this slide we are telling that is the producing inclusion free steel is next to impossible. Basically, if you think that I will produce a steel completely free of inclusion, it is next to impossible. It is not possible at all, because there are very tiny inclusion that cannot float up to the top. So tiny inclusions are there, millions of tiny inclusions are there in the steel, but fortunately very tiny inclusion does not hamper the mechanical properties of the steel. But little bigger inclusions like 10 micrometer and above, they can have a bad um, effect on the mechanical properties of steel. And such inclusions are also, there are numerous inclusions, like there are several inclusions can be trapped into the liquid steel because they cannot float to the top during this processing of steel. So they get physically entrapped. So there is the concern. So you can see this diagram from where you can find there's a number of inclusions per centimeter cube of steel. So you can see the order. So per centimeters cube, it is order ranging from 10 to the 3 to 10 to the 9. So per centimeter cube, so much inclusions and inclusion diameter. Obviously, if you increase the inclusion diameter, then their value are decreasing, but still you can see beyond 10 micrometer also, you have significant amount of inclusion of the order of several thousand that you can find. And this amount of inclusion increases obviously when the total oxygen in the bath is higher, because higher the total oxygen, higher is the inclusion. So you can see these values are given. So now from the gist of this curve is that, first of all, number of inclusion present in a small 1 cubic centimeter could be 8 millions of 1 micrometer size. So you can see, if you see the 1 micrometer size, then it can be several millions of inclusions. Fortunately, there doesn't have much deleterious or adverse effects on the steel, but there are numerous such, billions of such inclusions are there. And if you consider the 10 million, the 10 micrometer inclusion, 10 micrometer inclusion, if you can see, then their orders also can be several thousands. That is, the several thousands can be there. The 10 micrometer inclusion also can be several thousand in 1 centimeter cube of volume. And beyond that also, there is the 10 to 50 micrometer inclusions are not good inclusion. They are quite big, right? Bigger inclusions are harmful, and therefore concept of clean steel is connected with controlling the inclusion. Now think is that these 10 micrometer to 50 micrometer, these inclusions also, lot of inclusions are staying into the liquid steel. They are not being able to get away from the system by floating or whatever it may be. So think is that you have to live with this inclusion also. So what to do with that? Then you have to control the inclusion. Control by inclusion means if you can change their size, say morphology, composition, such that they doesn't become too much, their harmful effect is reduced or eliminated, right? So that is the thing. There is a tailoring this inclusion by size, say morphology, is attempted to reduce the adverse effect of such inclusions during the downstream processing of steel, or during its and their on the service life. There is the property on the service life, like fatigue property and all these things, such that fatigue property is very much influenced by these inclusions. So the inclusion control is very important. You have to modify the shape. This is called the inclusion modification. Okay, so that I am telling, that is the producing of inclusion free steel is not possible. We have to live with inclusions. Okay, there are several new millions of tiny inclusions, very tiny. Those are not very harmful, but 10 micrometer above, they are harmful. So we need to modify them. We need to what is that? Modify their size, shape, distribution. We can tailor their size, shape, distribution and composition such that they doesn't have much deleterious effect in during downstream operation or as well as in their future life in service. Second thing is the impurities and inclusion. Basically, why? There's basically it is the impurities. If you have a large impurity in the steel, you will have large inclusion in the steel. So control of impurity is very important. So Basically, impurities like oxygen, phosphorus, sulfur, hydrogen, nitrogen and carbon should be very ultra low level. You can make this impurity to a very ultra low level, then obviously your inclusion formation will also be less, because the endogenous inclusions are the more inclusions, large inclusions, okay, and they are basically produced by the chemical reaction between these impurities. So, production of clean steel basically attempts to reduce these impurities to a very ultra low level. That is what we can do, such that we can stop the inclusion formation. And these impurities, as I said, and the steel making technologies over the years has made a great accomplishment in reducing such harmful elements over the years. You can just see that this impurity, and even by 1995 we have achieved a significant improvement. That is, the sulfur could be reduced just above 1 millimeter. There is a ppm level. We can reduce the sulfur to 10 ppm level. We have achieved during 90s. Okay, and all other elements, right, can be reduced to 10 ppm. You can see that is the nitrogen, carbon, phosphorus, oxygen, everything can be reduced to 10 ppm level. We have even achieved by 2000, right? So now by this time also we have been able to bring down all these impurities even less than 10 ppm level. So very ultra low impurity still we can produce, and when you can produce that, we can reduce the impurities, that is the inclusions, significantly. And those inclusions that cannot be removed, we can also modify them according to size, shape, morphology and your composition, such that they do not have adverse effects on the future application, future life of the product in operation. Now, inclusion modification. Now, what do you mean by inclusion modification? This is the steel. You can see as cast condition MNS. MNS is one of the deleterious inclusion in the steel, and they are called the manganese stringers, because when you roll the steel, then they become very flat and long, and that is called stringers. So, as cast, this is the manganese stringers. Manganese stringers look like this, and when roll it, it become further elongated, and this is the thing. They are very soft and deformable, that is why they become elongated. But thing is that they are the point of weakness, because in that region the matrix is very weak, because they do not have much strength. So, okay, they can allow the propagation of cracks easily through them. Okay, so this is the roll steel. And then alumina inclusion you can find is they can make a very aggregate of alumina inclusion, because alumina inclusion are hydrophobic. You can say they do not weight by the liquid metal too much, but the two alumina inclusion try to combine together, because thing is that there the surface energy get reduced rather than their association with the liquid metal. Association with the liquid metal surface energy is high, but when two solid alumina inclusion combine, then the surface energy get reduced. So that's why the alumina inclusions try to flock together, and that's why big alumina inclusions are found. So this is one of the network of the alumina inclusion as cast alumina inclusion, and when you roll it, then they become this type of irregular and small number of inclusions and very hard inclusions. So their hard inclusions are point of stress concentration, because inclusion, as the name suggests, because inclusion and matrix always there is a very weak bonding between them, because they are not very incoherent, and bonding is also very weak, and under stress also this bonding become further weak, and then causing a void between the inclusions and matrix, and they are the point of stress concentration. So inclusions, these alumina inclusions under rolling condition, they are very irregular, rough, hard and randomly distributed inclusion they become, right, these small inclusions. And these two inclusions, the manganese stringers as well as the alumina inclusions, are not good at all. But if you treat this type of steel by calcium, if you add some calcium, then what happens? This calcium modify this deleterious inclusion to a spherical inclusion. That is interesting. And by calcium treatment, you can form the calcium alumina is converted to the calcium aluminate, and this is in the core of the inclusion you can find. And all the calcium sulfide and manganese sulfide, they make solid solution, and then they come over it. So manganese sulfide, calcium sulfide on the surface of calcium aluminate, okay, as a ring, as a nice sulfur ring is there. You can find a perfect spherical inclusion you can form, and that basically eliminate the stringers as well as this alumina, raw, randomly distributed strong alumina, because these calcium aluminates are some of the calcium aluminates like C12S7, and then some calcium aluminates are liquid and they are easily deformable. So, they form a liquid calcium aluminate, and over that you have the sulfide ring is there. So, these inclusion, these spherical inclusions are deformable, and they are soft, deformable and spherical now. So, that is why you can get rid of this bad inclusion by a very nice inclusion, and this inclusion does not hamper the mechanical properties significantly. Okay. So, that is why this is called the inclusion modification. We are just changing, you can see how the shape has been changed into a modified inclusion. Okay. That is why it is called a inclusion modification. That is, by calcium treatment, manganese stringers and irregular hard alumina inclusion is converted to global soft deformable inclusion with calcium aluminate at the center and sulfiding at the periphery, right. So, now this is one of the mapping of such inclusions, and it is done by Boschak et al. One of my student worked with this thing, and you can find that here you can perfectly found a sulfur. When you mapping the sulfur in the across the inclusion, we can find the sulfur is present only across the periphery. You can find a perfect sulfur ring. Okay. So, this is the inclusion which is the best inclusion, because with the surface sulfur ring, and inside you can find there is the calcium is there, as well as you have calcium is there, alumina obviously will be there. Okay. Aluminum is there, this is the aluminum, and calcium is there, calcium aluminate, and oxygen obviously will be there. So, calcium aluminate is there at the core, and at the periphery you have a sulfur. This is from the ACM, what is that? There is the elemental mapping. Now, if you see the phase diagram also, binary calcium oxide and alumina phase diagram, here you can find it is not only 2, 3, numerous several calcium aluminates forms, and at different temperature, out of which 3, that is the tricalcium aluminate, you can say 3COL2O3, it has a melting temperature of around, you can see C3A is melting temperature 1668. So, melting temperature is Kelvin, basically all are Kelvin. 1668 means minus 273. So, that is 1873, less than 1873. 1873 is the Kelvin is the steel temperature, liquid steel temperature. So, we can find the 1668 is much less than 1873. So, at steel making temperature C3A, that is the 3COL2O3 is liquid, Ca is also liquid, and then you have C12A7, that is also C12, that is your 12CO7L2O3 is also liquid, then 3COL23 is also liquid, COL2O3 is also liquid, it is very marginal, around 1873 is melting temperature. So, all these three basically 12, but it is called basically C12A7. C stands for calcium oxide, A stands for alumina, and then you can say C12A7 is liquid, then C3A is also liquid, Ca is marginal 1870, so you can say liquid. So, liquid calcium aluminate at 1600 degrees centigrade, you can consider Ca, C3A and C12A7. Other calcium aluminate are not liquid, they are solid. Okay. So, these are the inclusions, those will be soft and deformable. So, this type of inclusion we intend. So, your calcium to aluminum ratio has to be maintained in such a way such that you can form this type of inclusion, this type of calcium aluminate which are liquid at steel making temperature, such that they become very deformable and soft inclusion. Okay. And also this, if you can produce the liquid calcium aluminate, then you can reduce the nozzle clogging also. It has been found that nozzle clogging is a phenomenon where basically these alumina network, the alumina inclusions, coral shaped aluminum inclusion basically block the nozzle. So, if you treat with calcium aluminate, those alumina can be converted to calcium aluminate and liquid calcium aluminate. As a result, they can release the nozzle. So that is also another advantage of calcium treatment. It avoids the nozzle clogging by converting the alumina network to a calcium aluminate, liquid calcium aluminate, and then release the nozzle also. So this is the thing. So calcium treatment does two things. One thing is that it produces the liquid product of deoxidation, calcium aluminate. Some of them are liquid. So as a result, you can get rid of nozzle clogging. Besides the liquid inclusion you can form, they can coalesce and then they can form a bigger inclusion and go away from the system also. And besides those inclusions that cannot be removed from the system, they can also be converted to a soft deformable inclusion. Okay. So that is possible by calcium treatment. Now I will talk about this is the calcium treatment, and I will talk about the carryover slag and its effect on the inclusions. Role of carryover slag on the effect of inclusion, because during the tapping of liquid steel from LD to the ladle, invariably some of the LD slag that gets entrapped, that gets that pass through with the liquid metal into the ladle. That is called the carryover slag. A portion of LD slag is carried over to the ladle during tapping, and that is called the carryover slag. And it is usually formed because of the funnel shape vortex formation. You know, that is in a everyday, it is our everyday experience in the kitchen. You can find if you pour some water at the end, when the liquid height becomes less, then there is a piercing sound is there and vortex is formed and the liquid moves through the vortex. So, and then the vortex has a very strong drag force. As a result, that is, the slag also can be dragged along with the metal to the sink. So, there is the formation of funnel shaped vortex causes the slag to flow out with the metal during the latter stage of tapping when the metal height is low. So, it is our common experience from that from kitchen sink. And interestingly, this carryover slag, what is carryover slag? There is the LD slag, as you know, it constituents, major constituents are FeO, SiO2, P2O5, MnO, CO is also there, right? But among them, this FeO, SiO2, MnO, P2O5, they are reducible oxide. They can be easily reduced, right? If you add, because in the ladle, when you do the deoxidation, the bath oxygen level become very low. As a result, this oxide in the slag will be very unstable under low dissolved oxygen. What will that? Because their vapor pressure will be comparatively higher, so they will dissociate. FeO, especially FeO, will immediately dissociate, and then it will be reduced, and the silica also will be reduced, MnO will be reduced, P2O5 will be reduced, everything will be reduced under deoxidized bath, because when the oxygen level is very low, they will not be stable at all. So the LD slag at the top of the metal bath, when you deoxidize the bath, they will not be stable. As a result, what they will do? They will basically consume the deoxidizer. Basically, unnecessary aluminum will be converted to L2O3, and the silicon will be reduced to silicon. Silica will be reduced to silicon, Fe will be reduced to Fe, MnO will be reduced to Mn, P2O5 will be. So, all the reversion will take place. From the slag, they will enter into the metal and they will enrich the metal with the impurity. And a lot of aluminum consumption will be there. That's why that will effectively reduce the yield of aluminum also. Okay. So that's why the carryover slag is not good. Besides, basically they can change the inclusion scenario in the liquid metal also, and liquid metal inclusion scenario, and also they can allow the refractory dissolution, because the composition will change into the bath. As a result, refractory also, a new equilibrium between refractory metal and slag will be established. So in that case, some refractory dissolution also can take place. So that's why the slag carryover is not good, because this LD slag basically increases the oxygen level into the liquid bath. Okay, because they will be reduced, and then increasing the oxygen level in the bath. You can think that way. And when the oxygen level in the bath increases, then the refractory also can dissolve. Okay, they can behave differently. And also the increase the oxygen level in the bath, that will, what will happen, they can also, this extra oxygen during the solidification, they will precipitate out the oxides, right? So that way inclusions will be there. Now, problems of arresting the carryover slag. Now, how do you do that thing? Basically, a plug shaped refractory peaks is usually how to arrest this carryover slag. During this process I have talked about, but here I will talk little elaborately. Thing is that a plug is used, and that is called a dart, and it has a density between the metal and slag. That is, it has a density greater than that of the slag, and it has a density less than that of the metal. So, such that the plug can be dragged when the funnel will form, the plug can be dragged and it can close it before the slag can start draining off. That is the idea. But placing the plug and where you will keep it, it depends on lot of experience and all this thing. So, as a result, you cannot completely stop the slag, you cannot completely stop the slag to enter into the ladle, and that is, in other words, it is very difficult to make a slag free tapping even if you use the plug also. Basically, the idea is that the plug will move, will be dragged towards the nozzle and it will block it before the slag come, and its density is just in between that thing. That is the way. But it is useful, but it cannot stop the slag to a great extent. Then we use the electromagnetic censure, because if you use the censure, then when the slag will start coming into the drain sink, the signal will suddenly change and you can stop it. But that improves little, but still carryover slag cannot be stopped completely. So, although it is difficult to make the slag a slag free tapping, carryover slag can be minimized using a dart or electromagnetic sensor. That is possible. Typically, I am just giving some value. Without dart, if you do not use the dart, then the carryover slag can be of the order of 10 to 15 kg per ton of steel, 10 to 15 kg per ton of steel. But if you use a dart, then it can be reduced to 4 to 5, significant decrease, actually from 10 to 15 to around 3 times you can decrease the slag carryover using the dart. And if you use the electromagnetic sensor, then it can be 3 to 4 kg only, and further you can lower it down. But you can find in spite of everything, 3 to 4 kg of slag will come along with the metal. So, Ashok et al. Recently reported a core model simulation and dimensional analysis of the drain sink formation during the tapping process. He has a PhD thesis also, his publications I have noted here. And based on a cold model simulation, this is the photography of the drain sink formation from a video camera that is placed just in the liquid, and from there you can see this is the drain sink formation. This is the white portion through which the metal and the slag will come, and this is the center portion is the bubble, that is the vortex. Okay. So, this is the drain sink formation, and they concluded, that is the Ashok concluded, that that is the critical height for the vortex as well as the drain sink formation, because this vortices basically forms for a particular liquid height. Okay. As I said, in the simple kitchen sink also you can find when the liquid height become reduced to a certain height, then only it forms. Similarly, here also we have studied what is the critical height for the vortex formation and the drain sink formation. Basically, vortex finally converted to a drain sink. Okay. So, what is the critical height for the vortex and what is critical height of for the formation of drain sink, and we have found there is a design parameter has a great role to play there. But as far as if you consider the yield of the liquid steel or the carryover slag, how much of slag will be carried over, they mostly depends on the nozzle diameter, and it depends on your physicochemical properties of the slag like surface tension, viscosity, also amount of the carryover slag at the top. So, this is their observation, and they also make some hypothesis basically that if you tilt the ladle, basically if you dislodge the vortex from the nozzle, then also you can have some benefit. But anyway, they have not been able to study, actually in the cold model simulation they do not have any rotating device such that they can see whether really if you tilt just when the border there is the drain sink is forming, if you tilt the vessel, whether the drain sink can be dislodged. They have not been able to demonstrate by cold model simulation, but they have given a hypothesis. Anyway, So now finally, I will talk about the ladle refractory and its inclusion and its effect on the inclusion, because you can see in contrast to the primary steel making and in case of the secondary steel making, primary steel making what? That is the slag in the secondary steel making. This is the very important, that is the, if you consider the, in contrast to primary steel making, the slag in the secondary steel making is deoxidized, okay, and contains high amount of Cu and Al2O3. That is the difference. The slag composition is totally different in primary steel making, secondary steel making. Primary steel making, it is mostly FeO, SiO2 and P2O5, like that thing. FeO is significant, around 20% FeO may be there, okay. But so dissolved oxygen is quite high, but in case of the secondary steel making, FeO is not there. So it is totally the slag composition is completely different. So refractory also has to be taken care of, because you have to see those type of refractories, those does not react too much when the dissolved oxygen in the bath is very, very low, okay, such that they do not decompose, okay. So that has to be there. For example, if you use a silica refractory, acidic refractory, that is silica refractory will not be suitable actually when the bath oxygen is very less. Silica will immediately decompose, right. Second thing is that in the primary steel making, the choice and design of the refractory is governed by the lining life and the cost of the process and all these things. In addition to that, in case of the secondary steel making, you also have to give attention on the quality of steel because of the refractory, because refractory mechanical and chemical erosion is very important, and that depends on what is the property of the refractories, okay, it depends on the property. That is the, to reduce the mechanical erosion, what is there, because it is because of shear stress of the liquid and the refractories, okay. The refractory has to have very good wear resistance, such that they do not wear off very much, and the thermal shock resistance also have to be very high. If their shock resistance is not good, then they can crack and the liquid can penetrate, and then they can, mechanical and chemical erosion will be more, right. So those are the properties are very important. I will talk to that. So because finally it is the chemical attack. If the refractory get react with the liquid metal and the slag significantly, then they will introduce impurity into the liquid metal. Okay. So that's why it is not only the lining life. Here the important question is quality of the steel is also important, such that the refractory does not interact too much with the metal and slag. That has to be seen. Okay, then secondary steel making, that's why I say it, in secondary steel making, in addition to this factor, quality of steel is one of the major concerns. The lining should be stable and inert to the liquid steel. That is what I am telling, okay, because the quality is very important, because secondary steel making is the final stage where you can control the inclusion. Beyond that, it is not. So lining should not contribute significantly to the inclusion formation. So lining should be stable and inert to liquid steel. A low thermal conductivity refractory is desirable obviously everywhere. There is the lining, the refractory lining is that conductivity should be low, such that it does not allow too much of heat. You can conserve the heat. That is the basic idea of the refractory. Okay. But thermal shock resistance is also important here, because if you do not have thermal shock, if you make cracks, if spalling take place, then it will increase the inclusion. If you crack, then the liquid also penetrate, and then more chemical and mechanical erosion will take place. If you spalling also, then also a lot of refractories will come into the liquid steel in the form of inclusions. So, but again these two, low thermal conductivity and good shock resistance, this is also very counteracting. It is very difficult to get in the same material. From this point of view, silica is a very good one. It has a good thermal resistance, shock resistance, thermal shock resistance at the same time. Okay. So your thermal conductivity is also okay. So not very high. So from that point of view, silica can be used, but problem of the silica is that under deoxidized bath, the silica will dissolve into the metal. It will increase the, it will come to the metal. Silica will be reduced, okay, and silicon will be introduced into the metal. So that is the thing. And erosion of the lining increases Erosion of the lining, obviously erosion of the lining increases the exogenous inclusion, but corrosion of the refractory introduces undesirable impurities. That I am telling, corrosion, like if silica is the silicon will come, otherwise, and also oxygen, dissolved oxygen will increase. So, your lining, refractory lining should not contain any amount of the silica. Okay. It should be very inert oxide like alumina. Alumina is a good one. Alumina is not, does not have much reactivity like silica and all these things. So, alumina can be okay, but silica impurity wise also silica should not be there. If silica is there in the refractory lining, then it will dissolve, it will increase both the silicon and oxygen into the bath. So, tar bonded, basically tar bonded calcine dolomite is used, COMgO lining is used, okay, with less than 3% impurity. You see the impurities are not there, because usually dolomite contains a lot of other impurity like silica and all this thing. They should not contain impurities. If impurities are there in the lining, they will be introduced into the hot metal, right. They will introduce the high dissolved oxygen will also be introduced, and then elemental impurities also be introduced into the liquid bath. Okay. Ladle cover, porous plug and slide grate, these are made of the high alumina or magnesia refractories. Usually high alumina magnesia refractories are used because they are much inert compared to other oxide. MgO, alumina, calcium oxide, they are much more inert compared to silica, other. FeO, if FeO is there in the refractory, it is not tolerable. FeO silica should not be there in the refractory in a very low level also, because if they are there under deoxidized bath, everything will come into oxygen, they will increase the bath oxygen, okay, and this is not good. Okay, these are the references, and conclusion we can say inclusions are inevitable, they will take place. Modification of inclusion in terms of composition, size, shape by treating with calcium reduces the adverse effect of the inclusion, or deleterious inclusion like alumina, manganese stringers could be converted to globular, soft deformable calcium oxysulfide by calcium treatment, and they does not hamper the further processing as well as service life of the product. LD slag carryover into the ladle decreases the yield of deoxidizer and enriches the melt with impurity and inclusions. So, that is the thing, there is the LD slag carryover is not good, because LD slag carryover, LD slag contains lot of reducible oxide like FeO, MnO, SiO2, all these things, and under deoxidized bath all are susceptible for reversion because they will get reduced and join the metal phase. So, that is why slag carryover is not a good thing, and it has to be reduced significantly. And with slag carryover, that is the impurity scenario into the liquid bath completely changes, and also new equilibrium between alumina, there is a refractory slag and metal can be established and causing lot of dissolution of the refractory wall also. In secondary steel making, the choice of refractory is primarily governed by the quality of the steel. It is primarily governed by the quality of the steel, unlike in the primary steel making where main thing is the refractory lining, but here your think is that the quality of the steel should not be affected. So, it should not contain any reducible oxide into the refractory lining like FeO, SiO2 should not be there. Only the refractory lining can be made by alumina, calcium oxide and the magnesium oxide. Okay, those are comparatively inert. Okay, this is all what I am to say. Thank you very much.